Hello, this is Lewis again. When I was teaching as a vocational instructor, many of my students presented some interesting problems, be if they were in the workforce for years and been out of high school for years, or even recent high school graduates. Imagine trying to teach a largely, at least technical subject to students who had no basic knowledge of science. Our education system has little use for actual science, and I mean the science that you can apply to the real world. Most high school science today consists of some watered down biology that, yeah, everybody knows what a T-Rex is, everybody knows what climate change is, but they can't tell you how long ago T-Rex lived or what the world has gone through since T-Rex went away. So this little video here is going to introduce you to how we know the temperature of the past and how this applies to practical, usable things. So let's begin with some of my little possessions. This is an ancient piece of mudstone. This is a little fossil, and this probably lay on some beach millions of years ago. And this little creature, I think it's a brachiopod, died on this beach. He got buried, and he became a fossil. What became mud and sand and whatever fused into a fairly hard rock, not ridiculously hard. This was because of a mineral called calcite, or calcium carbonate. Okay, what is that? Let's look at another fossil. This is another fossil from my collection. It is largely limestone, but if you could actually zoom in and see, there are hundreds and hundreds of little seashells. This was produced by various living creatures millions of years ago in some long gone sea. The idea is I can't tell you, you can do two things with studying these type of fossils. You would want to know how old it is, but even better, what was the temperature in which it was formed? What was the temperature that these little living creatures lived under? Now, temperature determines what creatures live there, how many, and so forth. So how do we take the temperature of a fossil? There's no such thing as there is a fossil thermostat, or at least an indicator, that checks out in the real world. Let me be very clear on science. Science is an explanation of the operation of the natural world. It has nothing to do with your feelings. It has nothing to do with religion or deities or political decisions. It has nothing to do like that. Science is three things: data, data, and data. You have to go by what you find. You can't alter the data. You can't make up data. And you can't make the data, try to twist the data to support your beliefs. So let's look at how this happens and why I have a problem back in my electrical and electronic classes that students didn't know what atomic structure was, that many high schools or trade schools don't teach any of this because they figure wrongly, and these people can learn this if given a chance, they figure you're too stupid and you don't need to know this. You're not stupid, and yes, you do need to know this. Let's look at the atomic structure of oxygen, the center of this discussion. First, a little basic theory of atoms. we have a positively charged nucleus where we have protons and neutrons. The number of protons determines what the element is. 8 protons is oxygen, 7 protons is nitrogen, 1 proton is hydrogen, 3 protons is lithium, and so on. In most atoms except hydrogen 1, one isotope of hydrogen, they always have neutrons. A neutron is just a little bit heavier than a proton, but when we say atomic weight, we add the number of protons and neutrons together. Then we have electrons that orbit the atoms like planets around the sun. This drawing here really inflates the size of the electron. By weight, a proton weighs 1,800 times as much as an electron. Electrons have a negative charge, protons have a positive charge, and when you have equal numbers of electrons and protons, the overall charge is neutral. There is something important to know, though. Again, atomic weight is the number of protons plus neutrons. Oxygen comes in 3 stable isotopes in nature. We're only concerned with 2. Oxygen-16 with 8 protons and 8 neutrons, and oxygen-18 with 8 protons and 10 neutrons. This begins to suggest already that oxygen-18 is heavier than oxygen-16, and indeed it is. In chemistry, we have a unit we call the mole, M-O-L. It is the basis of all your chemical reactions. It also tells us the weight of particular elements. So 1 mole of oxygen-16 is 16 grams. 1 mole of oxygen-18 is 18 grams. So the difference in weight, molar weight, is 2 grams. This illustration shows what we're dealing with. If oxygen-16 weighs less than oxygen-18, then water molecules with oxygen-16 are going to weigh 2 grams less than a water molecule with oxygen-18. This is differences in weight, and this is important for a number of reasons. Let's discuss something to put this in perspective. If you went to your stove and you put a quart of water in a pot and you boiled the water until it was half gone, if you check the molecular weight, you would find, by the way, oxygen-16 makes up about over 98% of all the oxygen. Oxygen-18 makes up less than 1%. But when you went through that boiling process, you will find out that you now have a higher concentration of the heavier oxygen-18 water molecules than you did the oxygen-16. Why is this? It's heavier. It has a slightly higher boiling point. So this begins to give you some ideas that because they have a slight difference in boiling point, how they sort out in nature depends on temperature. Give you an example. If you go to California, precipitation usually moves from the Pacific west to east, and it moves up the Sierra Nevadas. As it cools, the heavier oxygen-18 water molecules will condense before the lighter oxygen-16 water molecules. So it starts to rain. You'll rain out most of the oxygen-18 molecules, as where the lighter oxygen-16 water molecules will end up falling as snow or ice further up in the mountains. By looking at the ratios of oxygen 18 to oxygen 16, and by many laboratory tests, we can tell approximately what the temperature was, either in the oceans or when the ice was formed or whatever. Now, what does this have to do with my seashells or my seashell fossils? Oxygen is also found in calcite, commonly called limestone. All right. Organisms in the ocean will take dissolved calcium. Calcium is always dissolved in the oceans. It will take carbon dioxide and water, and it will use the oxygen from the water and the carbon dioxide to make one calcium atom, one carbon atom, and 3 oxygen atoms. We can take limestone and again, through analysis, we can tell the ratio of oxygen 16 to oxygen 18. What does that tell us? What practical use is this? We can tell what the climate was millions of years ago, and we can track changes in climate over millions of years. Here is an approximation of temperature changes over the last 542 million years. 542 million years ago, we had the Cambrian explosion. That's when life, multi-celled, complex life, burst onto the scene in very large numbers. And it was far warmer then than it is today. About 450 million years ago, we had really a lot of glaciation and ice form during this period. Let's go over, okay, here is the Permian, end Permian Triassic extinction occurred in here when a volcanic eruption in what is today Siberia covered 2 to 3 million miles of land with 4 miles deep in lava. Really poisoned the planet, and something like over 90% of your life went extinct. Here's your Triassic and Jurassic and Cretaceous. These are where you're going to find your various dinosaurs that everybody loves to watch eat people on television. In here is your Cretaceous, in Cretaceous extinction. This is about 65 million years ago, when they believed a 6-mile wide asteroid slammed into the Yucatan in Mexico and pretty well wiped out the dinosaurs, even though several very reputable people were saying many of the dinosaurs were dying out before this. That's still a controversy that goes on today. 50 million years ago, I think this is the Paleogene, you notice the temperature up in here. This was I guess your emergent. This was 15 million years after the dinosaur extinction with the meteor strike, and the globe was mammals abounded. The world was full of life after all that earlier destruction. The planet was covered with forests, places that are deserts and tundra today had vast forests, trillions of animals. Mammals abounded all over the place. That's all. Now we come closer to where we are today. After that period, probably starting about 32 million years ago, we began a steep dive in temperature, glaciation. And if we go over here to 0, we're coming here today. The climate is very cold today, way below the geological norm. When this happened, your forests died out, your grasslands, desert, and tundra expanded, a lot of animals went extinct, and that's how we know what the temperatures were. If the temperatures actually warmed back up in here, the Earth would be far greener, wetter, and better off than it is today. Of course, that's going to deal with sea levels, but that's going to be another lecture. Here's a closer look at our temperature changes since the extinction of the dinosaurs 65 million years ago. Here is the peak Eocene period. I guess it was the age of mammals arose at this time, and you had forest all over the world. I mean, you had vast, lush forest in places like Wyoming, Nebraska, Australia. There were virtually no glaciers or ice on the planet at the time. And again, it was widespread. Ask yourself, which is better? Would you rather have forest like you have in Appalachia, or would you rather have desert and scrub like the Utah desert? Then, beginning approximately 35 million years ago, we enter the Oligocene epoch, and the temperatures have been steadily dropping, but then they sort of nosedive. If you notice, again, they're measuring the constant percent based on the percent of oxygen 18 in the samples they're studying. Like I said, normally oxygen 18 forms well less than a percent. But as the temperature cools, that percentage increases. Why is that? Remember I discussed the snow and rainfall in the Sierra Nevadas? Because by this time, glaciation was going to start. Prior to this, there wasn't much ice in Antarctica. After this period, it greatly expanded, dried out the planet, dropped the temperatures, and caused a lot of extinctions, and a lot of forests died out. So what happens is the lighter oxygen water began to fall as snow and was accumulated as ice in Antarctica and elsewhere, leaving a higher concentration of oxygen 18, and that's how they plotted it. And that's how they plot the temperatures, the remaining oxygen 18 versus 16 percentage. And of course, this is way down over here today in our present oceans and water systems. From 2.5 to 5 million years ago, as you can see up here in this picture, there was virtually no ice in the northern hemisphere. Sea levels were higher, of course, because whatever. And of course, the climate was greener, warmer, and wetter than it is today. Even with the huge if we go look over here on your right, how warm the climate once was. Then starting between 3.1 and 2.6 million years ago, the temperature began to nosedive considerably. It went from warm, wet, and green to today, and you'll notice that most, particularly the last million years or so, has been about 3/4 of it has been cold, very cold. Cold does a lot of things. It creates droughts. It kills off a lot of stuff, cuts down photosynthesis. It drops ocean levels, and so forth. If you look through here, and this would be modern times, and that's not correct up in there because it turns out the temperature actually dropped over the last 2 years, but that's another lecture. You can see that if we were to return to the earlier warming, the planet would actually be much better off in the biological sense. But again, all this ice and glaciation is highly abnormal, but it's the world as we have it, and we find this out by looking at the ratio of oxygen isotopes. So again, I hope that gives you an idea of basic geology, some earth science, and a little bit of chemistry. Thanks for listening.